Okay, well, we've been representing complex numbers in this form as a plus bi. In this section, we talk about alternative representations. We could simply consider a plus bi as a pair of real numbers, ab, and we could plot this pair on an xy plane. Now, this is called a rectangular or Cartesian representation, and you can see an example here. Here are three complex numbers plotted in a plane. This is called the real axis. This is called the imaginary axis. So 2 plus 3i is 2 along the real axis plus 3 along the imaginary axis. So I think you've probably seen this before. So again, we can think of complex numbers as points in a plane called the complex plane. We can also think of complex numbers as vectors. Just like we think of points in a plane as vectors. Okay, so you could draw a vector. You could consider this point here, identify that point there with the vector that's drawn from the origin to that point. And we have a vector notation here, I and j. I is the unit vector along the x-axis, j is the unit vector along the y-axis. So here we make the point that that really we're talking about, in some sense, the same thing in three different ways. We can talk about complex numbers, we can talk about points in the plane, we can talk about vectors. We really are conceptualizing the same thing in three different ways. And you can call this kind of identification between different representations an isomorphism. And we'll be seeing many examples of this in the future. All right, now there's also a polar form of complex numbers. If you take a point in the plane, here's this point a plus bi. We can also represent this as the point a comma b in the plane. Think of the angle from the x-axis and the radius out to the x-axis. So we can characterize this complex numbers by this pair of numbers r theta. So r theta is called the polar representation of the complex number a plus bi. R is called the absolute value or modulus. Okay, you get that from the Pythagorean theorem. The distance here is the square root of a squared plus b squared, and you remember that's how we define the absolute value of a complex number, as the square root of the real part squared plus the imaginary part squared. And this angle is called the argument, or complex argument, of this complex number. Okay, so here we're just using some trigonometry, that a plus bi, the x component, is given by the cosine of theta, or r times the cosine of theta. The y component is given by r times the sine of theta. If you draw this triangle, you'll see that. And this shorthand notation, cosine plus I theta, we write that as cis theta cosine plus I sine. So we can write complex numbers in polar form in this way, r cis theta, where r is the absolute value and cis theta expresses the argument. And you should be able to use trigonometry to go back and forth between the two representations, between the polar representation and the Cartesian representation. And here's actually a formula for the complex argument in terms of the real and imaginary part of the complex number. You can prove this simply by drawing the triangle and seeing that the tangent of the argument is equal to b over a. Okay. So if you want to do these problems to convert from to rectangular form from polar form, you can use trigonometry. All right, look at this example, for instance, that here we have 2 cis pi over 6. Okay, what does 2 cis pi over 6 mean? There we go. If I wanted to do this one, 2 cis pi over 6, if I was going to draw this in the plane, Well, I know the radius is 2 and the angle is pi over 6, so let me draw an angle of pi over 6. And the distance out here is 2. Now, if I want to find the rectangular form, I'm going to want to find the base of the triangle, and that will be my A, and the height of the triangle, that will be my B. So that's A and that's B. And you can find A and B using trigonometry. Okay, and I guess that's all I'm going to say. You can take this triangle and work out what A and B must be using this angle and this radius. And these other problems are done similarly. Now, to go backwards, you simply draw the picture again and work out the angles. For instance, 1 minus I means I go 1 along the x-axis, or real axis, and minus I along the imaginary axis. So what I'm going to have to figure out is the angle of this point from the x-axis. So you could draw it this way. So the question is, what is this angle? And that's going to be your theta. And then you also want this distance, that's going to be your r. So you're going to have theta and r. And the answer is, once you find that, then your answer is whatever r you find times cis of whatever theta you find. Okay. This exercise gives some kind of relationship between geometry and complex numbers, and it's something that you can explore. Now, one of the usefulnesses of polar form is it makes it very easy to multiply complex numbers. Here's a formula that you will be using many times. You multiply two complex numbers, you multiply their moduli, or absolute values, and you add their complex arguments. Multiply the moduli and add the arguments. Okay. And so this is writing them as complex numbers. This is writing the individual complex numbers in polar form. Okay. The proof of this fact uses these trigonometric formulas that we're not going to prove in this class, but this is from trig, and you can look them up in your trig book. And here we ask you to go through and fill in the blanks of this proof. Okay, we don't actually give the reasons over here, but this all comes out from the definitions and simple operations that we've done before. Okay, so see if you can fill in the blanks for that proof. Okay, also want to divide complex numbers. All right, now in this discussion we talk about division of complex numbers in polar form. And the way we're going to get at division is similar to the way we did before. We're going to look for multiplicative inverses. And we work through these exercises to see that here you're given a z and you want to find the multiplicative inverse of z. So you're going to find several multiplicative inverses, and then you're going to generalize your results. And using the multiplicative inverse, that will show us how to actually divide numbers in complex polar form. All right, so we'll let you work through those exercises to get that. And in the end, you have this formula for the division of two numbers in complex polar form. So multiplication, division is summarized here. Okay. And some more exercises. All right, now here's another common operation, is raising to powers. Okay, how do you raise a number in complex polar form to powers? And this is another great example of the usefulness of polar form. If you raise numbers in rectangular form to powers, you get a very complicated formula that involves the binomial theorem. But if you raise a number in complex polar form to a power, you have this very simple formula. R cis theta to the nth power is the same as multiplying the modulus to the nth power times cis of n times the complex argument. Okay. Now this is a general proof for different values of n, where n can be 1, 2, and so on. And in many cases that you want to prove something like this, you use a technique called induction. You prove something for n equals 1, 2, 3, and so on. What you do is you prove it first for 1, and then if you prove it's true for n, then it's also true for n plus 1, etc. So here we give an example of how you go through a proof by induction. Okay. Actually, we want to prove an infinite number of statements. Okay. The first statement is obviously true. It's basically the identity. The second statement comes from, you're actually simply multiplying 2 together. You can show that. The third statement could be proved on the basis of the second statement. So here's a fill-in-the-blank proof for that. Okay. So, and we could also prove the fourth statement and so on and so on. And that would take an awful long time. So what we want to do is, suppose it's true for the nth statement, then we want to show it's also true for the n plus first statement. In other words, if we have the nth power of r cis theta has this form of r to the n cis n theta, we want to show that from that it follows that the n plus first power of r cis theta has this form of the modulus to the n plus first times cis of n plus 1. Okay? So if we prove this statement for general n, this is for general n, and prove also for n equals 1, that's enough to give all the proof for all n. It gives a proof for all n. Sorry, I had to move that over there a little bit. Okay. So you prove the statement for n equal 1, prove the statement that if the statement for n is true, then the statement for n plus 1 follows. Then if you have those two parts, then you have the proof for all possible values of n. Okay, so here's the summary of how an induction proof works. Prove the statement for n equals 1. Assume the statement for n is true. It follows that the statement for n plus 1 is true. All right, and here we go through the actual details. Okay, and here's some examples of how you use that result. Very easy to compute powers of complex numbers using de Moivre's theorem. Okay, and I think that's pretty good for this section, and we'll stop here.